Hi, this is Glenn Lipscomb. I'm going to be talking about how to use Aspen Energy Analyzer. To start the program, click on the Start icon down here at the bottom, the little Windows icon. Then click on Aspen HySys in the list of programs. Open up that folder there by clicking on it, and then you want to select Aspen Energy Analyzer. Click on that, and you'll start the program. This window here that asks you to start a video or register, you can close. The window behind, which is the Aspen Energy Analyzer program, you can maximize. Very first thing we're going to do is create a project, a heat integration project. You can do that one of two ways. Either click on Features and HI Project, or click on Managers and go to Heat Integration Manager. I'm just going to click on Features, click on Project, and start up a new project, and then maximize that window. And this is where you begin. This top part up here is illustrate some of the heat curves that we've talked about in class. What I'm going to do is come down here, move the cursor down so I can get to the point where I can reduce the size of that and increase the size of the area we're going to put in the stream data right here. We're just going to type it in directly using the example we covered in class. Another way to input the data is to click on File, or over here to, File, Manager, Heat Integration Manager. It's not underneath that either. You can click on File and import results from, actually it's here. I was looking in the wrong spot, so I have to follow along here with me. But if you click on this icon right here, you can transfer data from an Aspen HySys simulation, or from an Aspen Plus simulation, or from an Excel file. So there's these three icons right here that you can use in order to transfer data. We're just going to type in the data that we had in class in this area down here where it says click on underneath data here, process streams. We're also going to specify utility streams. We're not going to change anything underneath economics here, although we will review that. So underneath process streams, the very first thing we're going to do is from that table we had, that first example, we're going to type in a name for the name H1. And then where it says inlet temperature, we're going to type in for H1, the inlet temperature or the supply temperature was 520 Kelvin. If you type in 520, it shows the temperature as C. I'm just going to change that to K by clicking on the down arrow and selecting K, and it converts Kelvin to centigrade for me. The next item asked for, the next piece of data, is the outlet temperature. The target temperature is 380. Once again, that's Kelvin, so I'll change that to Kelvin. The MCP value that we need to put in here from the notes was 200 kilowatts per Kelvin. Well, let's see what units we have here. We have watts per centigrade, which are the same as watts per Kelvin, but we don't have kilowatts. So in order to convert the 200 kilowatts per Kelvin, or 200 kilowatts per centigrade, we have to multiply this 200 by 1,000. So it's 200,000, 200 with 1, 2, 3 zeros after it. Now we can choose this to be watts per centigrade, and it'll be input correctly. What it does, it calculates the enthalpy change associated with the stream in kilojoules per hour. It also has a heat transfer coefficient. If you click on this, we can change that and override it, double click it. We can choose a heat transfer coefficient from some other source. If we have it, at this point, it's not too critical that we input this heat transfer coefficient, a more accurate value. We could just click on default, for instance, and then just close this, and that'd be fine. Next, it asks for flow rate and a specific flow rate and effective heat capacity. I'm just going to put in a value of 1 here for the effective heat capacity in the units of kilojoules per kilogram centigrade, and just let it do the calculation of the flow rate from the value of MC sub P. These are not too important for what we're doing right now. So we got the first stream entered. We're going to repeat that for the second one, H2, which had an inlet temperature of 490 Kelvin and had an outlet temperature of 460, or target temperature, in the wrong area here. Gives me an error there because I had put in the wrong temperature. So what I want here in stream H1 is 380 Kelvin. And it's working. I believe it's working. Let me try that again. 380 And let me try selecting Kelvin again here. That's correct. So 460 Kelvin for the next one here. That was the one I wanted to put in. I was typing it in the wrong spot. MC sub P here is 300 kilowatts per K. So that's 300,000. 1, 2, 3 watts per centigrade. Now note that it converts these MC sub P values from units of what we entered to the units you see displayed here. They got converted to kilojoules per centigrade hour. And the way it did that is it multiplied by 3,600, the kilowatt hour value by 3,600. So let's move on next to what we need to specify. We're just going to put a value of 1 here for the effective heat capacity. Then move on to our next stream. Next one is going to be cold 1, C1. The supply temperature for this is 450 Kelvin. We're going to heat this up to 510 Kelvin. And MC sub P is 600,000, 603 zeros. We'll make that watts per centigrade. And finally, I'm going to put a value of the effective heat capacity of 1 over here. The last stream involved is C2. It has a supply temperature of 300 Kelvin and a target temperature of 350 Kelvin and an MC sub P value, or F times heat capacity, of 100,000 watts per centigrade. And finally, I'm going to put an effective C sub P of 1 in here. So it's good at this point just to review that, make sure you got everything put in correctly. So we have our supply and target temperatures. Unfortunately, they were in Kelvin, so we'll have to, if we point at this, it will tell us, if we point at temperature, it'll tell us in centigrade and Fahrenheit. It won't tell us in Kelvin, but I think looking through this, I can tell you that these are indeed correct. If you want, you can pause this and compare to what you're doing if you're following along, but I'm just going to assume that you have put this in correctly. Okay, so we have our process streams in for the data. Next, we're going to have to put in utility streams. So let's click on utility, and we have to select utilities from a drop-down list that's provided here. So we'll click on the down arrow, and we can see we have a number of different utilities. We have air and cooling water for cooling. We have a fired heater to go up to 1,000 centigrade or to 2,000. We could use hot oil, which goes up to some upper temperature, or different values for, let me click on that again, or different values for high pressure steam, low pressure steam, medium pressure steam. Without the word generation, that means you're supplying heat. With the word generation, that means you're taking a stream and producing steam from it. So, and then there's other options here. You can look at those if you want. Well, certainly we're going to want cooling water, so we'll go ahead and add that in here. And here's the default values that it has for the cooling water in terms of inlet temperature and outlet temperature, which are fairly reasonable. If you want to, you could override those and change those to something else. The other thing we need to choose then is a way to heat, and we have a choice between high pressure steam, low pressure steam, medium pressure steam. If we choose medium pressure steam, we'll put that in here, it tells us that the inlet temperature, the maximum temperature, is 175 that we heat a stream up to. Let's click on the process streams and see how high we need to go. We want outlet temperatures for C1 to be 237 centigrade. We want to reach that temperature. If we use a utility, let's come back here on the utilities, this medium pressure steam utility cannot reach 237. It's higher than the supply temperature. So we don't want medium pressure, we want high pressure steam. That goes up to 250. And so 250, let's go back to the process stream, is higher than the 237, and it's 13 degrees higher. So it does provide a temperature difference, an approach temperature greater than 10 degrees if we were to go use high pressure steam to heat up to 237. And then that's all that we need for utilities. In the economics area, it provides information on how it does the economic calculation in terms of a rate of return on investment. They want 10%, a plant lifetime 5. We're not going to go through these variables right here. Hours of operation, as well as how it's doing the calculation of the heat transfer, the capital cost for the heat exchanger. So we're not going to delve into that anymore. I'll just click back here on process streams. Now, one final thing is that the DT min, our approach temperature, is set to 10, which is the value that we've been using. Okay, so once we got all the inputs put in here, if you notice up here, this composite curve is what we generated in class, except it's been flipped. What we had on the x-axis is now on the y-axis, that's temperature, and vice versa. What's on the y-axis that we had was enthalpy is now here on the x-axis. But you can see the curves, I think you can imagine them, and rotated do look similar. And we have options of showing other curves. We could show what's called the grand composite curve, which we did not talk about. Then there's also some other curves here, general plot curve, which really is not meaningful for us. Really the most meaningful one is the composite curve. If we point at this composite curve, we can change how the graph looks, the values. I'm not going to do that, change the graph at all now. Okay, so we are now ready to have Aspen Energy Analyzer suggest a heat exchange network for us. And the way we can do that is by clicking down here on the bottom where it says recommend designs. So I'm just going to click on that. And it comes up here and it asks us for some parameters for which it has default values. First off, it asks what's the maximum number of times you're willing to split each of these streams. And I'm not going to change that. It's currently set to 10, but we could change that to anything we want. It also says what's the maximum number of designs you want me to try to generate. And so we're going to leave that at 10. And then you can, at this point, preview your input data. You can come back and have it pop up just the stream data you put in. I'm going to close that. You can have it pop up the utility data that you put in. I'm going to close that. And you can also pop up what's called forbidden matches. If you, for some reason, don't want to have a heat exchange between H1 and C1, you can click on this X right here to forbid that, and likewise for any of the other combinations. So with that, we'll have one more thing. Let's look at tips. Tips here are things that you should probably know already. One is that you want to keep, this first one may not be familiar, but keep stream segmentation to a minimum. What this means is splitting a stream up so that you can more accurately calculate the heat transfer in a heat exchanger. So segmenting the temperature change, the enthalpy change into different sections. For instance, if there's a phase change, that might be very important. If you're going from a liquid, a subcooled liquid, to superheated vapor, there will be changes in heat transfer coefficient that you might want to account for. And so if you want to help increase the speed at which it generates a network, you can forbid matches. We're not going to do that. We're not worried about speed here. We have a very simple example. And these last two are things we have talked about. There must be at least one hot utility that's hotter than all the cold streams, and one cold utility that's cooler than all the hot streams. So let's click back on General. And I think that we're okay with this. We'll click on Solve. And lo and behold, it comes back with several designs that have been generated, and it says that it could not generate the number of near optimal designs. We had asked up to 10, but there were other designs that so that it said there may be other designs that that it could not find. That was pretty far away from the optimum. So let's click OK. And we're going to look at these designs up here in this top part. Underneath scenario 1 here are 4 designs that were generated. And these are all labeled design 1, 2, 3, 4 with the A in front of it. If you click on design down here, this is just what we put in. This is a diagram like we talked about, in which this blue arrow indicates, first of all, the utility, the cooling water going from its inlet temperature 20 to 25. And the solid red line down here represents the steam, the high pressure steam that will go from 250 down to 249, just a 1 degree temperature drop. The dashed lines are our process streams. So for instance, this red line is a hot stream. We're cooling off from 249 over here to 106, 107. And the other streams you can see there. If you just point at it, it'll give you the information regarding them. So what we're going to do is we're going to look at the designs that are over here. We have 2 designs that have this yellow square in back of the symbol. These are infeasible designs. So if I click on this, you'll see that these dots indicate heat exchangers that are connecting either a utility at the top or a utility at the bottom. to one of the process streams. So for instance, these two blue dots connect a cold utility to a stream we want to cool off, and these two red dots connect down here a hot utility we're connecting to a stream we want to heat up. But these silver dots here represent process streams that are connected, for which it's a feasible design, and these yellow dots represent ones that are unfeasible. And if you look into this in a little more detail, you'll find that they're unfeasible. There were two feasible designs. This A design 4 right here, and you can look at how it connected the two hot streams H1 and H2 to the utilities. So H1 got connected completely to the cooling utility, whereas H2 was split into two parts, in which one part was contacted with stream C2, and another part, in fact, this contacting between H1 and C2 provided all the utility that was needed for taking this cold stream and heating it up. Whereas so that provided that entire utility. But if we look at C1, which was we needed to heat up, its energy is being provided solely by this heating utility, by the steam here, the high pressure steam that's condensing. Whereas you can look up here how the cooling utility was distributed among the two cold streams or hot streams we had here that were cooling off, and you can see how they decided to split that up. Now, how it did this? Well, it went through a program in which it tried to find an economically minimum cost to minimize the cost of performing these heating and cooling operations by contacting the streams together or by using utilities, and it factored in the cost of the heat exchangers based upon the economics that we talked about earlier. So for this particular design right here, down here in this lower part, it talks about a summary of it. It shows for this particular configuration, the heating utility that was required, the cooling utility was required, and what percent of the target values that it was looking for. And so these target values right here they're not shown here, but this is a percent of the target. These are the minimum heating and cooling utilities. I'll go back and talk about how we can get those from the analysis in a moment. And then from these, so this shows you that for this particular design, the heating was almost 2.5 times greater than the minimum, and the cooling was almost 3 times greater than the minimum. But the minimum achieving the minimum utilities would not minimize the cost of performing this heat transfer because of the heat exchanger cost. And if you look over here, you can see that for this particular design, the capital cost for these heat exchangers was a little more than $1.5 million. And the minimum cost for the heat exchange was would be roughly twice this. So we're getting close to the minimum cost. So let's go back to the heat exchangers themselves. We click on that here. It shows us the cost to run these things and in terms of utilities and operating costs, as well as the area that's required of them. You can see one is very, very small, 0.12 square meters. And it did a heat exchanger design, and it looked at multiple shell heat exchangers in order to do the calculation, and then the overall load on the heat exchangers here. And then finally it has a summary of the utilities. These are utility values and percent in terms of the load, percent of the target. So what I want to do is come down here and look at the targets. These are the minimum utilities that are in this box over here, minimum heating and cooling utilities that we would get from these composite curves or from the temperature intervals. And if you change these units from kilojoules per hour to the units that we were talking about in terms of kilowatts, you'll find that the heating is indeed equal to, if we take our value of 15,000 kilowatts, that would convert to the 5.4 times 10 to the 7th kilojoules per hour. Interestingly, if we look at these two designs, I'll click on design A4 and then design A3 to compare the two, is that these aren't anywhere near the designs that we looked at, in which we minimized the extra utility that was needed. We minimized the cooling and heating that was required in order to accomplish this heat transfer. And based upon the calculations done here with the cost of the heat exchangers, it turns out that you don't want to do that. Those heat exchangers that are needed in order to minimize utilities don't give you the minimum cost. And so it will be sensitive to how you price the heat exchangers, but these designs right here give you a way to, or using Aspen Energy Analyzer, you're able to take into account the cost of the heat exchanger, as well as that of the utilities. Now for any one of these feasible designs, if I click on design, let's say design 3, and I decide that I want to try to optimize that to reduce the cost associated with this particular design, make sure that Aspen reached the minimum cost. If I click on it, then up here in the icons you see here, I can click on Open Optimization View, and then I have a couple options to optimize. I can either minimize the total annualized cost or minimize the area. Let's click on Minimize Total Annualized Cost. If I click OK, it's going to ask me, it's going to go through and check and make sure it's possible to do that. If I click Run, it tells me optimization was successful. And then the optimum design 3 in terms of annualized operating cost is here. If I click on that, we look down here, total cost. The total cost after optimization was 0.1021 dollars per second. If we click on just design 3, before that, it was 0.1074. So we were able to save a little bit of money through that additional optimization step. And you can look at the two designs and determine for yourself what happened when we did that. What I want to do before we stop is I want to go back to scenario 1, click on scenario 1 up here in the list, and then all the designs that we looked at are summarized in the tab down here at the bottom that says Designs. And so if you look down here, it shows us the total annualized cost for all the designs that we looked at. Design 3, Optimize, had the lowest cost, the annualized cost. You can compare the area, so even though 3 had the lowest cost, it had used the largest area. If you look at this, it looks like it's 1.049 E00. It's not really E00, it's E04. You have to pull that over there to show all the digits. Then over here it shows us the heating and cooling cost as well, and then this is the operating cost associated just with those heating and cooling. So this is the operating cost contribution to the total cost over here. The difference between these two is the annualized capital cost right here, which is associated with the purchase of the heat exchangers. And so with that, what I'm going to do is turn this over to you and let you have fun with it. You'll be using this for your project. One final thing, if you want to save this, you can click on File up here and then Save As. I would recommend that you save this to your desktop on the virtual computer. So I'm going to click on Desktop and type in Test and type Save. This will save it there. And then from your desktop, what you can do is you can connect to your OneDrive account and then transfer it to your OneDrive account. And so with that, I'm going to conclude. And if you have any questions about how to use Aspen Energy Analyzer, please ask me. And if we need to, we can set up a Blackboard Collaborate session in order to do that. Bye for now.